Hello, how's everybody doing tonight? Hopefully you can see me. Hopefully you can hear me. We are live on the WebAssembly North America YouTube channel. We are checking for your comments, and throughout the night you can feel free to put your questions into the chat on the YouTube video, or you can head over to the WebAssembly Discord, and there is a Wasm NA channel. And if you hover over that channel, you'll see a chat button. And that's where you can also ask questions. So tonight we're going to have a presentation from Roberto from StackBlitz. He is going to be presenting about Rust and WebAssembly threads. And it's a pre-recorded talk that we will play for you, and then Roberto will be around to answer questions after the fact. So with that in mind, I'm not going to waste too much time. I'm going to put the talk up on the stream, and please remember to drop your comments, questions into the chat. Oh, and it looks like Roberto will also be in the chat answering questions as well. So that's great. Let me just remove this thing. There we go. All right, so let's get this rolling. I'm going to
Hey, thank you all for being here today to hear what I have to say about some stuff we've been working on and that we love working on. Sorry, I cannot, give this talk remotely, but live. Um, I'm based on Europe, and that would be tricky for me given the time frame. But at least I'm, live in the chat, so I get a chance to interact with you all. And I also want to apologize because I don't have the equipment for a recording of a certain quality. I went through the whole pandemic without giving a single talk, stream, or podcast. So I don't really, I was waiting for in-person events to come back, and here I am giving a pre-recorded talk. And about that, I actually want to try something. So I wanna try. I'm going to try to make it as spontaneous as possible. So I'm going to record in a single take if I'm able to, and I'm not gonna try to edit out my mistakes. So it's gonna be a little bit more. See, this is not a recording for posterity. This is a recording for you at this moment, and I'll be on chat to laugh about how cringy the recording is going. But anyway, yeah, I'm gonna talk about Rust, WebAssembly, and the WebAssembly Threads API and our experience with it, building some stuff that we're building that in particular targets the web. So this talk is going to be biased towards the web as the host for our WebAssembly. And it kind of also makes sense to focus on the web for something I will talk about in a second. My name is Roberto, and I work at StackBlitz. I'll say what StackBlitz is about in a little bit, but for now you can stick with I'm a Rust person, and I very much love working with Rust and with WebAssembly. So what I'm gonna do three parts. First, the diff, which is the minimal amount of knowledge you need to understand what WebAssembly threads are about, so you can go ahead and apply that knowledge in the future. So that's gonna be really short and low level. Then I'll do an interlude on why we care about threads and what's our use case, and then we get into the field report proper, where also some stuff that we've been building. So the diff. If I wanted to go and summarize the spec, the WebAssembly Threads API spec, I wouldn't be able to because this is actually an iframe, and it's full of to-dos, and yeah, let's do that whenever we feel like it. it's not ready yet. The spec is actually not ready yet, even though this has shipped in production like years ago. Browsers shipped this API years ago and other runtimes as well. But the spec is not fully there yet. And it doesn't matter that much because this spec is written by the same folks that did multi-threaded JavaScript in the JavaScript specification. So everything, anything that is missing, you can pretty much guess how it's going to work by reading the JavaScript spec instead. So it makes sense to follow the steps of JavaScript. And that's yet another reason to maybe focus a little bit more on the web browser, web browsers as the host when we talk about WebAssembly threads. I'll maybe say something else about other runtimes later. So what is new? If you take your baseline knowledge of WebAssembly without knowing about anything about this new API, the stuff that is new can be summarized in 3 bits, which are the notions of agent and shared memory, atomic instructions, and the memory atomics wait and notify. What is this thing of agents and shared memory? Well, it's a big to-do on the WebAssembly spec, but you can more or less guess by reading the JavaScript specification that we're going from the host being described as something that interacts with the abstract machine, an instance of the abstract machine, to the host as something that interacts with several agents, each of them an instance of the abstract machine, which, by the way, this is something you can already do. You can spawn many threads in your runtime and run WebAssembly in each one of them, or many workers in your browser, whatever. But the truly new thing is that these agents can affect each other through shared memory, which is a new primitive that is verified in this shared flag in the text format, WebAssembly text format. And just with that, we have new stuff to build upon. For instance, let's take this really simple module that is about exposes a function that loads a number from memory, adds one, and stores the result back into the same place in memory. So you could take this module and create several workers on the web, for instance, several workers which map to threads roughly, and send them, the elements to create an instance, run the function several times, and print the result at the end. So if it weren't for this new addition of shared memory, this would be like pretty standard, and we would get like 100,000 printed 3 times. But by virtue of this memory being shared and the external memory object that is being created actually being set as shared, the semantics of this program are completely different. Now, different workers affect the same places in memory, and the results will reflect that. The results are actually kind of nonsensical because, well, this is out of order and their executions are interleaved. So this is new, but the end result is somewhat nonsensical because we expect the last worker to print 3 times the iteration count, and that's not what happened. Why is that? Well, you might be familiar with synchronization problems in other programming languages or at low level in your CPU or compiler. If you're not, let's just say that once you introduce shared memory and concurrency, you're opening the door or the proverbial box for a new kind of bug where the layers below you, the runtime, the compiler, the CPU are all conspiring against you and trying to change the meaning of your program. Unless you very much explicitly tell them, actually, this interaction with memory is supposed to be synchronized with maybe other workers. So you have to be very explicit every time you intend to read or write into places at the same time that other workers. This hints that we need something else apart from shared memory. We need a new type of instruction, atomic instructions that codify these semantics. So here, this is the actual right thing to do. We just use an atomic instruction that signals add 1 to whatever is in that address. And now we get a consistent value. These instructions, if you are, this is normal stuff if you know about the typical shape of low-level atomic instructions in CPUs. If you're not, this is what it looks like. a bunch of operations that you can use when you are building concurrency primitives. This is not the whole story, because actually you can build some concurrency primitives, some synchronization primitives with this, but it's not enough. You can build a spin lock such as this, where you can get several agents to agree on mutual exclusion for some resource by agreeing on an address that works as the lock. But this is very inefficient because you just rely on a loop that goes over and over until you are able to acquire the lock. So something is missing. And the stuff that is missing is a way of hinting or, well, instructing the host to affect the way the host schedules those agents in the same fashion that you would do in your operating system. This is modeled, these two new instructions are modeled after the Futex API in the Linux kernel, if you happen to be familiar with that. But this basically means, wait means, please block me, the agent, until I have something to do, because right now I don't have anything to do. And notify is a tool for other agents to indicate, well, whoever is waiting on stuff to do, please awake them, because now there's the stuff to do. And with this, you can actually build a proper mutex that you can lock and unlock. Now you no longer spin endlessly. You actually go to sleep when it's needed by using these primitives. So this is the whole story. This is what the threads APIs are about. It's about agents and shared memory, atomic instructions, and the memory atomics for waiting and notifying. With this, you have a better understanding of what the threads API is about, and you can understand how higher level primitives map to low level WebAssembly. So now is the time to maybe build something higher level. But first, I'm gonna tell you why we care about this new thing of WebAssembly threads. I work for StackBlitz, which is in the online IDE business. A fancy way of saying doing your programming in the browser. If you do your programming in the browser, there are several ways you can do that. One is maybe this thing I'm calling thin clients, where the browser is just a poor man's SSH client connecting to a full development environment installed on the cloud, either your cloud or somebody else's. And this works well within its set of trade-offs, and it's a very popular approach. But you might be less familiar with the idea of playgrounds. You've seen playgrounds maybe as a tool to explore a given programming language or a compiler on the web, maybe a JavaScript playground. But if you happen to be a pure front-end JavaScript developer, a playground is actually quite close to a full online IDE experience, because running your code is as simple as sticking it into an iframe and seeing it work. So you can leverage some clever cross-window APIs in the browser to build a fully self-contained online IDE if you only work with pure front-end JavaScript. And that's actually what StackBlitz was about until recently. We were a competitor in this playground space, but not so much of that lately. Okay, I've shown you two approaches, so now I'm gonna try to think about a third approach that would combine the strengths of the two. The remote, the thin client remote machine approach is more versatile because you can run arbitrary code. You're not constrained to front-end JavaScript, but you need a persistent internet connection. On the other hand, playgrounds, apart from being self-contained and not necessarily needing this internet connection, also have some advantages. You as the IDE author have full control over the user experience. You own the edit, run, debug, deploy lifecycle, and you have lots of opportunities to improve the user experience, to provide something more coherent and wholesome, so to speak. So yeah, what if I could build a fully self-contained in-browser development environment that runs arbitrary code? That's somewhat surprising, but since you are all interested in WebAssembly, is not that surprising, I guess. And that's exactly what we are about today. We released something called WebContainers 2 years ago, and it's been in production since then. And this is what we're about today. This is possible because we're trying to fit a square peg into a round hole. The square peg being all I need to run a development environment, something that looks like POSIX to run arbitrary code, into the round hole being the web browser. But if you squint, like, the primitives are there. You have web workers, we've seen them already, and that could map to user processes. We have shared array buffer, which is the primitive that is, within a shared memory. You encounter a shared array buffer on the JavaScript side, and that allows you to create an in-memory file system that is actually accessible from all processes, and they all get a coherent view of the same content. And if you want to do, beyond toy examples, if you want to do, for instance, server-side development, you can build a somewhat functioning networking stack by leveraging the service workers API that allows you to manipulate the networking of the browser to some extent. So yeah, all the pieces are there, and this thing can actually be built. Well, we built it. But also, we try very much for this to be practical. This is not a tech demo. This is something we intend for users to use to work on their daily jobs. This has influenced a lot a lot of our technical decisions. For instance, we just run JavaScript code for now. Wasm GC might change this, but for now we stick to JavaScript because we can reduce the virtual machine, etc. Even though this is a push forward from the status quo, because this is now arbitrary JavaScript code, not just front-end JavaScript code. We can run server-side JavaScript code as the one targeting Node.js, the main server-side runtime. And this focus on being practical is what drove us to WebAssembly and Rust. Just because you have a primitive to expose this shared in-memory file system to all your processes, it doesn't mean that it's going to be performant if you write that layer in JavaScript. Actually, we discovered something that is quite evident, maybe, which is that we absolutely needed the performance that Rust delivers. And also, like, Rust happens to be a language much more amenable to write these low-level components. So this is our use case for the WebAssembly Threads API and Rust on browsers. We are building quite an exotic system. I'm gonna cut. Hey, here we are again. So, now that we have an understanding of the basic primitives and that we know what our use case is and what we intend to build, let's get into the field report, where, I'll describe some of the stuff that we built and the fun parts that we found along the way. Fun meaning watch out for the warning, because there are curves ahead. I'm actually going to contextualize this to web containers and our product offering. This is the code flow IDE by StackBlitz. This is powered, of course, by web containers, and I'll be back to this in at certain moments of the talk. So let's jump into it. You wanna target WebAssembly with threads from Rust to deploy on the web. What should you do? Well, you need to do a few things. From the standard Rust to WebAssembly setup, you have to change a few things. You have to enable atomic instructions because the compiler is conservative and does not generate them by default. You have to use nightly so you are able to pass this flag, because the standard library for WebAssembly is not compiled with atomic support. You have to recompile it. So this flag takes effect. To recompile the standard library, you need to use nightly. There's no way around it. And you need to use Wasm NA. If you don't know Wasm NA, this is like the standard interoperation tool. So you can target JavaScript hosts from Rust seamlessly. So kind of kind of like a syntax sugar you drop on your Rust, so it's directly accessible from the JavaScript host. But in this case, it's not so much a convenience, but almost a prerequisite to do threads-based stuff. And the reason for that is somewhat arcane, but I'm gonna elaborate a little bit about it. It's about the weird state of the Wasm32 unknown target for the Rust compiler. This is the target of the Rust compiler we use, which is, you tell the compiler, generate WebAssembly code without assuming anything about the host. So what can you do with that target? You can, use collections and strings. That's easy enough. But what about like APIs such as file system or networking? Well, those are not available because in pure WebAssembly, there is no such concept. So all these APIs are stubbed out. They're either throw or they are no ops. If we were talking about WASI, the WebAssembly system interface that you might know about, these things would make sense, but that would be a different target. That wouldn't be WASI32 unknown. That would be WASI something. Because of the way the standard library is designed, this is a take nothing or everything approach. Like if you want some things in the standard library, such as collections and strings, you also need to bring in everything that does not make sense, such as the file system, networking, etc. And you just need to stop them out. This is the strange, weird way the WebAssembly target as it stands today in Rust is designed. This applies to some more other APIs. Spawning processes, accessing system time doesn't make sense. Pure WebAssembly does not have support for that. What about using atomics? Well, if you enable them with the flags we just said, yes, you have them available. ARC, if you have atomics, it's no longer an OOP. It's no longer a plain reference counted pointer. It's actually atomically reference counted by virtue of enabling atomics. What about synchronization primitives such as mutexes, channels, etc.? Well, atomic instructions include wait and notify that allow you to synchronize between agents. So yes, we have them available when you enable those flags. What about thread spawn? Well, we've seen nothing about creating agents. That's entirely left to the host. So strictly speaking, no, this is not available. You can't spawn threads from Rust code when targeting Wasm32 unknown. What about thread locals, global variables that have different values on each thread? This usually relies on thread-aware APIs of the underlying platform, but maybe we could something up if we are given a chance of manipulating the output of the Rust compiler. And yes, this is exactly why we need Wasm binding, because Wasm binding enhances the compiler support by virtue of being a post-processor and give us some extra goodies. This is not the only reason why we need Wasm binding. There are more things that wouldn't work without it, but this is maybe a good hint of why it's needed. So watch out. This mismatch between the underlying platform and the toolchain you're using is not specific to Rust. This is something you need to be aware of, whatever toolchain you use, either C or some other higher level language. Before we proceed into actually writing some code, there is something else you need to be aware of if you plan on targeting the web, which is about cross-origin isolation. If you try to do any Threads API stuff on browsers, you need to be in a cross-origin isolated state, because otherwise you don't have access to shared array buffer, which is the underlying primitive below shared memory. Actually, I think I can demonstrate this right here. Maybe, yeah. So shared array buffer. There's no such thing as a shared array buffer here. While if I go to There you go. If I go to code flow, yeah, it's there. So why is that? Why do we need cross-origin isolation? Oh, it seems that I'm frozen, but yeah, here I am. This is due to living in a post-Spectre world where having access to shared memory enables you to build something called high-precision timers that enables cool attacks where some untrusted content that you could load into your website could access memory that is not supposed to, given the execution model of JavaScript. So this cross-origin isolation thingy, which by the way, you can enable by setting some headers on the document and some headers on the assets you load, is a way of signaling the browser, we all trust each other. So it's cool if you give us these extra superpowers. This is simple enough for simple cases. Our use case is somewhat complex because you rely heavily on iframes and iframes on iframes that load third-party content, and getting everybody to agree we all trust each other gets more and more complex. So yeah, watch out for cross-origin isolation. And my recommendation is that you read the spec and then you read it again, because you will absolutely need to revisit this if your use case is complex enough. Okay, so let's go into actual web containers stuff. Web containers is partially based on WebAssembly and Rust, and one important piece, but not the only one, that we developed using Rust is the file system, as I mentioned before. This is a toy example of what a file system could look like in using Wasm NA and Rust. It's something that we load as a library in each one of those user spawn processes. This is a very naive implementation that is not quite what our stuff is more sophisticated, but yeah, you put something in static memory, a map of paths to content, and then you can expose a read function that takes a path and acquires the read-write log, and finds the path and returns the content converted to a JS value. So this is cool, and this is more or less like a 10,000 feet summary of the stuff that we do in Rust and WebAssembly. You should know that we are using synchronization primitives. We are using the read-write logs from the standard library and other third-party crates, and they just work if they happen to support WebAssembly atomics. They work, and everything is fine. How does this translate to? Oh, sorry. How does this translate? So here in the code flow ID, I can, echo something, and then yeah, a file is created, and I can edit it here, and yeah, there you go. Here's the content, and I can actually go into Node code. Oh, I set myself for failure. There you go. So the underlying pieces there are working there, providing us access to this in-memory file system. Now, this example leads us into something funny that you might need to be aware of, which is our web containers is a runtime. So all these different workers have access to this system, but the main editor that does not live on a worker, is just a web application, also needs somehow access to this shared file system, because you can affect the contents of the file system programmatically from user's code or from the editor itself by just writing. So yeah, the main document also needs access, but that's actually impossible. Let's try a little example here where I create a new shared array buffer. Oh, it's not a file. Huh. I'm not cutting for this one. So I'll just create New shared buffer. Okay, and I'll create a view because this is something you need to do. Array over the sub, and then I'm gonna try to wait. This is equivalent to the wait instruction of WebAssembly, but from the JavaScript side. View on 0 if I happen to find a 0. Oh, wow. Atomic wait cannot be called in this context. Why is that? There is this thing called the unblock flag that every agent has, every type of agent. So the main document is the type of agent that has unblock set to false, because by default, browsers intend you to use the main thread for the UI, and they don't want you to block the thread for whatever reason. You could still block it with a loop, but anyway, the API just doesn't work. So you can't just assume that your synchronization primitives from the Rust code can be called seamlessly from any agent, just some specific agents. The way to work around this is basically you either give up and actually communicate with a worker that does have direct access, or you use another API from the JavaScript side, which is called wait async, which is similar to wait, but instead of blocking the thread, it gives you a promise, which is JavaScript's lingo for a future, and does not actually block the thread. So, watch out, don't block the main thread. This is a constant in any GUI related programming out there. About those thread locals that we were discussing before, we use some thread locals in our code base. These are some just examples, like the current working directory, the controlling TDY, the controlling terminal of the process, the open files by the process. So these things kind of make sense to be unique per thread. And as we saw before, by using Wasm NA, we actually can use these APIs. So if I were to demonstrate this on CodeFlow, I could, there you go. I could maybe, I don't know. I'm gonna equal to bar, so I have something simpler, and then I'm gonna open a file descriptor, which is a unique thing to do with files, and that will give me file descriptor number 5. And then if I do happen to do the exact same thing, it also gives me file descriptor number 5, but they are, independent file descriptors. It just so happens that we keep a separate counter per process, which is the logical thing to do if you're familiar with these Unix APIs. Now, these thread locals come with a little bit of a surprise of their own. These thread locals, at the end of the day, each thread will need some space in memory to put that stuff, and actually that space has to be unique per thread because they're thread locals. They're global, but their value is different from every thread. And it happens that whenever threads die, they don't by default clean this space. They do on your operating system, but that's because your operating system knows about threads and knows about the life cycle of threads. But here, Wasm 32 unknown doesn't know anything about spawning threads. We spawn them manually by using workers, and Wasm Binding did some trickery to allocate a little bit of space for each thread, but there's nothing there that knows magically, well, a worker just finished, so I better go back into this chunk of memory and clean it. So we are leaking. By default, you could be leaking a lot of memory every time you use thread locals. This is usually not a problem for the use cases, the typical use cases for threads, because you typically, create a pool of workers and you have them there forever, and it's fixed size, so you don't leak because they don't die, they're alive forever. But our use case is about spawning workers, mapping user spawn processes, so it's at user's demand. So we very much care about not leaking this much memory. And so summary is, this is something we actually had to go and fix ourselves. So we introduced, among the experimental support of Wasm Binding for threads, there's the even more experimental thingy here where we exposed a function that you can, in a do-it-yourself fashion, use to clean this space and have a better, just don't leak memory. So, mind your threads, and if you happen to be spawning lots of different threads, try to understand how thread locals work and the problems you might have with them. And lastly, this is something that I actually like a lot. You can combine Async I/O with WebAssembly threads seamlessly, almost seamlessly, because Wasm NA does have support for it. So here, this is a bit of code where we are connecting threads to a particular thread that happens to receive all terminal output. And for that, what we do is that we combine channels that, so each worker has its own sender to send stuff. And then there is one thread, one worker that will receive all that data in an async loop that we spawn using the Wasm NA features runtime. And this basically leverages the event loop of the browser. So I just find mind-blowing that you can combine these two things as, with so little code and have it working. As an example of this, I think I could show, sorry. I think I would show maybe, yeah, we have a bar. So yeah, we actually, instead of terminal output, I'm going to show file watching, which is something that is also amenable to events. So other workers will have to notify, one worker will have to notify another that something happened with a file, and it needs to do it in an async fashion. So it makes sense to rely on this async stuff, async I/O stuff. So I'm going to watch bar, and every time something happens, I'm going to log ping. Oops, something is, read. And watch, obviously. Here we go. And then if we open bar here, for instance, and we save, there you go, save and delete, there you go. So this is actually leveraging this, it's actually happening by leveraging the native event loop, which is kind of cool. But this combination of using the event loop and together with a worker or an agent has some pitfalls. If you wanted to rely, you cannot combine them as seamlessly as you would like. For instance, this is just a made-up example, but imagine you would want to actually rely on a browser API that is asynchronous. So for instance, you want to fetch something from network and you want to do something with the response. And finally, when it's done, you want to unblock the thread. So, you want to make a request, block the thread, and when the request finishes and does its thing, resume the thread. Well, that's actually not possible. That's completely impossible because once you freeze the thread, the whole thing is frozen. The event loop is frozen, and async APIs won't progress. So this is kind of bad because most interesting browser APIs are async. So as a workaround for this, you either try to use async API instead, if it exists. Most of the time it doesn't, or you need to coordinate with another thread. You cannot do all this work together in a single thread. So this is also a very typical pitfall of combining the asynchronous nature of Java, of browser APIs with this new world of multi-threaded Rust on browsers. So no loop, no progress. So that was it. That's pretty much our field report. Some tiny bits of the stuff that we've built and interesting problems we found along the way. Well, at least we think they are interesting. They are certainly more interesting after you have fought them for long. As a summary, I would say that everything just kind of works. It's amazing that being the support for threads on the Rust toolchain being so experimental, still everything kind of works, and you can build a pretty complex and pretty significant system with it without thinking too much about the limitations. But you do have to think about the limitations from time to time. And actually, these are things we've encountered, some of these things that I just described, plus some other things that I didn't have time to elaborate. But yeah, we've run into our share of walls being bugs in browser implementations, WebAssembly runtime implementations, toolchain limitations, etc. But still, I think we are happy to live on the edge for this one and to be able to explore this space. There are actually a few things that would make our lives way easier. WebAssembly is one of them, but there are other WebAssembly specifications in Flux that we very much look with interest, such as better interoperation with JavaScript strings or better memory primitives. So, I'll just left this here in case you wanna investigate a little bit on your own. I didn't want to depart without saying a word or two about the elephant in the room, which is WASI threads. So WebAssembly threads alone is a very bare bones API that doesn't quite fulfill the needs of a toolchain such as Rust, right? You can just port multi-threaded code and modify it. You have to do a lot of do-it-yourself cooking, spawning all those workers and coordinating, etc. And we already talked about this. Many of the natural APIs you expect to find in a toolchain are actually fulfilled by WASI, the WebAssembly System Interface, and Threads is not an exception. And actually, just a couple of months ago, WASI Threads, the WASI Threads proposal was put forward. And once you adopt this proposal, things are way easier. And you can actually forget about many of the intricacies of spawning workers and whatnot. You can just use a different target. If instead of wasm 32 unknown, we'll use the, WASI threads target or something that's yet to be defined, and you'll be able to just mostly unmodified Rust code, and this will map naturally in other runtimes, which is the reason I haven't focused on, say, other runtimes like Wasm NA or Wasm Time, just because they are kind of waiting for this thing to mature and then adopt it fully. So yeah, that's it. I'm gonna leave you with a list of further reading in case you are interested. It's our blog with some of this stuff and a cross-origin isolation how-to, which I very much recommend if you are interested in targeting the browser, and some references on the stuff we've talked about, plus the mandatory call out for you to try WebContainers, because I do feel like, I still find mind-blowing that they work. I think it's a feeling that a lot of people get. So, anyway, thank you for having me, and I'll be happy to answer any questions on chat, and thank you for speaking with me.
All right. Hopefully you can hear me okay, because the audio on my own computer does not seem to be happy with me tonight. But I was watching the stream on another device, and it seems like the audio for the video at least came through okay. So hopefully it's just something to do with my headphones. So thank you very much to Roberto for not only recording that impressively one take video for us, and also thank you for being in the chat. I'm just going to highlight a couple of the comments that came through. So it was asked, so the entire file system lives in the memory, and yeah, that's the idea. The web browser is a magical thing. And then Python was brought up. Would this idea be useful for languages like Python, who really like the file system, as we, at Suborbital in our own experiments found very quickly. If Python doesn't have some concept of the file system, it gets very upset. And so, yes, maybe this could be a building block to help with other languages that really like to be able to read stuff from disk. it was asked if StackBlitz uses WASI, and I think WASI is generally, an out of browser specification, and so I think inspiration is always taken from the web side, the server side of WebAssembly, and in between, because there's obviously some shared concerns, but StackBlitz itself does not need to use it. So it was asked that workspaces can get quite large. So if the entire file system is in memory, that could be an issue. And I think, yes, I think that would be a problem. Luckily, a lot of machines these days have just oodles and oodles of memory, and then really fast SSDs for swap when the memory runs out. But it sounds like they have some mitigations in place, and maybe we'll see another talk about that sometime in the future. So I don't see any questions in the Discord. And oh yeah, we're also hoping for browsers to give us APIs to work with. I'm personally really excited for the day where WebAssembly can directly interface with browser APIs. That's one of the things that I'm most excited about, rather than having to go through a JavaScript environment to get there. I think that would be extremely cool, but one day we'll get there. And another question is, could IndexedDB work for this? And hopefully Roberto's answering the question in the chat, because I don't know a lot about IndexedDB personally. I think I've used it one time, and that was a long time ago. And while we wait, I want to mention that we are likely going to be taking a break for May for the WebAssembly North America meetup. But if you are interested in being a speaker, or if you are interested in seeing a particular person be a speaker, please let us know. You can find either me or Suborbital on Twitter, or now on Blue Sky, because that seems to be the things that everybody is excited about, or on Mastodon. You can email team@wasm.builders or team@suborbital.dev. They all go to the same place, and we will try to make that happen. We do have a question, or an answer to our question about IndexedDB. It could, but it might get tricky being async. I refer you to the no loop, no progress slide. Yeah, honestly fair. And sounds like Roberto is going to hit us up with some slides. You can tweet Roberto when you are able to upload those. You could maybe tweet at Wasm NA, and we will retweet that, or you can contact me or talk with Ramon, and we'll find a way to get those slides out there. All right, well, I think with all of that, we are wrapping up. Thank you, everybody who joined us live on the stream. And thank you to everybody in the future who's going to watch this as a recording. And thank you once again to Roberto for the presentation and for answering everybody's questions. And thank you to Ramon from the Suborbital team, who it's the middle of the night for him right now, but he did make a lot of this happen, organizing and working with Roberto on getting the talk together. Oh, one last thing. I think folks want to know if Roberto's on Twitter or Mastodon or Blue Sky or whatever else he might be on, or a blog, whatever it is. If you're still around, you can definitely put that plug in a comment, and we will get it up on the screen. Lots of love in the chat for Roberto's presentation. We'll give him another 10 seconds to put some social handles in the chat. Otherwise, we will tweet them or something like that. Yeah, honestly, Laura's right. It will probably be a different platform next week. Cool. First one to get WebAssembly trending on Blue Sky gets a prize. All right. I have a feeling that we missed Roberto, but I'm sure if you did a quick Twitter search, you would be able to find him. So I think we're going to call it there. Thanks everybody for coming, and we'll see you later. Bye-bye.